Oh, Chris, did you kick out the spammers?
I did.
Oh, good job.
Oh no. Okay. So
Good
can
to
you
There
see
we
my
go.
screen now?
Yeah, Tobias.
Does it work?
Yeah, I can see your screen,
Oh,
and
Oh, can you also
I will record when you're ready, Tobias.
try to carry? All right. So finally, we just lost Jason Fox, but that is fine. Yeah. So we have a problem in crypto. I like this is a very quick, condensed thing, and that is that both parties need to be online. And the solution to that already presented like in the past, and that is Bcash, a smart contract which allows offline payments.
I can't see the screen. If you're sharing a screen, Tobias, I can't see it.
You can't see the screen.
No.
I'm
It
can
says
see the
I'm
screen.
sharing. So
yeah, I'm able to see it as well.
you can't see it.
Dream Trove, I think this is the same problem you had before.
But
Do
I
whatever you
had
did
it before and then it went away. So I'm trying to figure out if there's like an option I have to click here or something.
Yeah. Anyway, I don't think the slides are too important right now. Maybe you can figure it out. Yeah. So the solution is B.Cash, which allows offline payments with the smart contracts. So, but we have another problem. Not everyone has, reliable internet. So especially like places like, I don't know, Central Africa or, there's the Burning Man festival, which also doesn't have reliable internet. And for that, we do have a solution, and that is fully offline payments. And there's a caveat to that. That's not at all in the product stage. Like we are, like I just had this idea and thought it was really cool to get people interested into smart cards. But I think it could be viable. Might be $1 billion idea, but yeah. How do we get out here? Is there a way to get out? Yeah. Just pull hard. Okay. So, we need to wait for me. Yeah. So Roscoe and I will guide you through that. Yeah, fully offline payments. So I will explain you how it works. It's a bit complex, but if you understand like some basic cryptography, I think it should work fine. Can you guys hear me fine, or is the connection good?
Yeah, it looks good.
Okay, awesome. So so how does it work? We have a card, and there's a private key on that card, and this private key it is basically sealed into like it's sealed in the card, and we can't access it from the outside. It's basically in its own universe where it can't and you can't extract it from the outside. We had like, I don't know, 40 years of engineering to make sure that the payments are really, and that the private key is really sealed behind that. But we can do computations with that. So we can derive the address from that private key, and then we can, release it from the card, like with some commands. Then we can, send funds to that address. And then that means in turn that the private key is now linked to those Bitcoin. Now the cool part comes in, where we want to send over the private key from one card to the next without without any blockchain interaction, and even without having like internet. And this allows these fully offline payments. And for that, we have two additional private keys. I call them internal private keys. One of them, like each of them in one card. So now we can, with these two private keys, they are also sealed in the card and can't be accessed from the outside. Like they are basically encrypted in there. Then we can do a Diffie-Hellman key exchange. Like has anybody heard of Diffie-Hellman? yet, or maybe do a thumbs up if you heard of Diffie-Hellman. Okay, I got 1 thumbs up. I mean 2 thumbs up, 2, 3 thumbs up. Okay, good. We do that Diffie-Hellman key exchange and generate a common secret. And this common secret should actually be like displayed on the card, but you know, geometry. And so like only card A and card B know about the secret. And it's like basically closed inside of the smart card. You cannot, like nobody on the outside world knows about the secret, just these 2 smart cards. And with this common secret, we can basically create an encrypted channel where the 2 smart cards can communicate with each other without anybody like being able to know what they're communicating with each other. Yeah, so with this encrypted channel, we can encrypt the private key on one card, delete it on that card. We also delete the internal. You also delete the internal private key. Otherwise, you could resend the cards. Then we send that over through any communication channel we want. We can actually send that over, I don't know, radio or internet or whatever, because it's encrypted, so nobody can, you know, decrypt it. And then we decrypt the key again on the other smart card, which also knows this common secret through the Diffie-Hellman. And yeah, we transferred the key. And that's basically all there is to it. Which way do we need to go? Right. However, yeah, and then that's linked to the coin. So, however, there are still some problems which you probably already, you know, immediately thought about. The first one is, you know, it kind of requires trust in the card issuer, because if some of them, you know, cheats and doesn't follow the protocol, they can just not delete the key and stuff, and that would be kind of bad. But what we can do there is just, you know, have strong audits and manufacturing and code, kind of what we do with Ledger and other like hardware that we kind of need to trust. And the whole thing can be open source. Like everybody can look at the code, everybody can look at how it's working, and that's not a problem. Another issue is that like the cards could fake deleting the key. So they just pretend to delete the key, and then you receive money, but you actually got double spent by somebody. So the solution to that is that we have like this cryptographic chain of trust of certificates, like a secret on the card, which is, you know, ratified by some authority. Oh, thank you. No kiss from you.
Doing great.
Thank you.
Go turn your phone or your computer. Go.
Oh, I still have energy, I think. But all right. So cryptographic chain of trust with that. Okay. Okay. Stairs. So the other issue is that another issue is that the certificate private key could get leaked, like the master key or stuff. If it's like on a piece of paper or something, and in a safe, then the safe could, you know, get broken into. But there, the solution is that we generate the private key on a card. I think I need to switch network in a second. The private key is generated on a smart card and then sent over in the same encrypted kind of way. So the so we just generate the private key on the card, which is possible because we have a you know, true random generator on there, which is kind of, you know, audited and stuff. So it always generates a really random thing. And then we transfer that over to the next card with this Diffie-Hellman kind of thing. So it never gets leaked out of the out into the real world. And then we have another issue, which is the granularity of the UTXOs, which is kind of inappropriate for commerce because you either send over $100 or nothing if that's your UTXO. And the solution to that is, you know, not yet solved, which is why the UX is not perfect yet. However, there were some really cool ideas by Richard, I just heard today, which is probabilistic payments. So you send over a bunch of UTXOs that are, slightly lower than the requested amount, but then you also send over some probabilistic payments, which are above the demanded thing, but due to they are only sent over with a certain probability, and this way you, you don't have the you can approximate, like over a certain number of payments, you get approximately that amount sent over. And it's kind of a neat way to go around that. I'm not sure if that's a good solution, but it's kind of intriguing to do that. So yeah, maybe one can go down that route. All right, there may come a day where we fix these problems, but it is not this day, so we just ignore all of those problems I just raised, and we just get right into it. So the battle plan is to do git clone of this repository. So if you want to follow, if you want to code along, you just clone this. I can put it into the chat, or is there any ideal place where I should put it?
It might be worth just like asking people if everybody,
I've already typed it, Tobias.
if anyone had questions about that, because there's quite a lot to take in.
Oh yeah, let's debate, maybe not debate, like maybe let's discuss this.
Definitely not in like too much detail, but
yeah, and I've been a bit
worth making sure that everyone just gets the basic.
So does anyone
concept.
have questions about this idea? I think you probably have, so feel free to ask, and feel free to ask dumb questions, definitely.
Well, I had a question about the UTXO granularity problem that you were presenting. I just assumed, and maybe this is a bad assumption, or maybe it's accurate. When you load the funds onto the card, wouldn't you go through like an intermediary wallet that could do like UTXO shaping, like control what the UTXO that's loaded onto the card looks like? Like, is that something you've thought of, or am I misunderstanding the problem?
No, the problem is the following. So when you send a normal Bitcoin transaction or Bitcoin Cash transaction, you can specify exactly the value you will send. However, when you send over just UTXOs, you are bound to whatever is specified in that UTXO. And of course, you can, do the whole bunch. Maybe you do like some Pareto distribution of payments in there. However, I mean, there still has to be like some kind of mechanism that determines like the distribution of that. And it's much more complicated than, just vanilla BCH, where you just say, okay, the amount is 500,053.75.
So when you spend a UTXO with the card, you have to spend the entire UTXO. You can't generate change.
Yeah, exactly, because you have like an exact. You send over the private key of that UTXO. This is the idea behind that, private key teleportation. So
you're not actually spending the UTXO in the traditional sense of because it remains unspent. So it's actually semantically wrong to use the word spend in a way, because it doesn't get spent on the blockchain. The private keys just get moved. So the UTXO on the chain stays exactly where it is.
It's like when I hand over a private key printed on a piece of paper to you and really pinky promise that I don't have any copy of that private key, except here you have technological proof that doesn't happen due to, like the limitations of like the benefits of the technology and stuff.
So this is completely offline transfer.
Yeah, completely. And this could work like in, I don't know, if you're on Pluto and want to send somebody over some money, then you don't have to wait like however many light hours for that payment.
So I am in an Amish community, so it is kind of like being in Pluto, so they're not online, right? I've been trying to talk them into Bitcoin here. So Jet says the Amish near him have cell phones, but these ones do not. So Yeah, I'm
That's
just
really interesting.
That's an interesting market I never ever considered.
Yeah, well, the thing is, their entire religion is based around decentralization, so it's really fitting. If people think it's based on being Luddites, but it's not. They're incidentally Luddites because they're decentralists.
Yeah.
So they can use electricity if they generate it themselves, right? But the problem is how to talk them into Bitcoin Cash, which I've been trying to do, right?
But I think this is kind of out of scope for this presentation.
Yeah, I
Useful
get
knowledge.
that. I get that it's out of scope. I'm just that's just
Yeah, it's a very interesting.
thinking.
Hey, Tobias.
Cool.
Probably need some more thinking. Hello.
Hey,
I just explained the whole thing.
Anyway, so I assume that the UTXO granularity problem is very solvable if you just prepare a bunch of small UTXOs in there.
Yeah,
but then there comes,
still hard, I think.
But then there comes a new problem. Assuming that all of this, especially the fake deleted key problem is unhackable, you just assume that. What would you estimate to be the requirement for the hardware of such a card?
Like
would you
what already
would you need a
exists
fair
off shelf?
Because I see some need to I see some need to manipulate UTXOs in there, for example.
Oh yeah, so it needs. Oh yeah, well, that's what you mean. Like it needs to do signatures. It needs to do Diffie-Hellman. It needs to do verify signatures at some point.
Yeah.
And it needs to be able to generate really random numbers and derive the public key from that. Yeah.
Right.
And
also
we've got cards that can do that.
Yeah, and also some sort of mechanism, which I have to admit I don't fully understand, that makes the receiving party trust that the sending party has not been hacked, and he really is deleting the private key per, trusting the manufacturer.
Yeah, but that that will be done by audits and stuff. So there's some higher level of trust involved.
Right. We assume that we trust the manufacturer. Yeah.
Yeah, we assume the manufacturer, because the good thing about this, all of that can be completely transparent. Like if a company were to do that, they would have to be like, okay, yeah, let's invite these people and they can look at the code. Like the code would be open source, but also the manufacturing would be open source. The loading of the code onto the card would be, open source and stuff. Or at least should be auditable on some level too. In that case,
right.
I think that would work.
And just to repeat what Toby said there, because Toby, your audio went a bit low when you said it, but basically those cards exist today. We all have one in our immediate vicinity in our SIM card. So it's like a standard Java card has those cryptographic capabilities, and you get the NFC version. So that's what's incredible. All the stuff that Toby's doing is with off-the-shelf cards that you can buy today.
Yeah, exactly. So we are going to use a simulator for now, because we have two cards and it's kind of hard to
in SLP USDH, or they're in BCH, but in denominated amounts similar to dollar bills, where you have one transaction for like a 20 and a 10 and a 5 and some ones.
Yeah. More like cash. Yeah.
Right, like normal cash, or printed cash, right? So it's where's the storage limit of the card? Because I thought they were sort of 2K.
Yeah, it can store, like the card I have here. I'm not sure if I can show it. It can store 100 kilobytes of data in the non-volatile memory, and and that is plenty for private keys and stuff. So you can probably store like 100 at least, maybe even 1,000 private keys on one of those things. Yeah, can grab it in here. The cool thing is like, oh yeah, there's one. Yeah. One of these cards, I think you've seen them already. You can buy them literally online. If you want to do this like at home, buy one of these smart card readers. They are relatively cheap. I think this one was more pricey because it has like 2 interfaces. But there are ones for like, I don't know, $20 or something.
The thing is that I kind of agree with imaginary username. So I think loading a bunch of unspams would be pretty interesting. But the thing is that I think it would probably be chain agnostic, right?
Do we have just plain water? Yes, it would be completely chain agnostic as long as the card supports the signature algorithm. Actually, yeah, it depends. Maybe even it would be fully chain agnostic depending on how you release the private key. Because you could either sign a complete, you could either sign the transaction, or you could just release the private key verbatim at some point and then delete it from the internal storage, so you can't teleport it anymore. So you could use this probably for a lot more things than just BCH, and maybe even more than for crypto and payments. I don't know.
Sure, as long as it's UTXO based, it's okay.
And another cool feature of this is that it's very private, because like if it's actually offline, then you have literally no trace of that, and actually the private key gets destroyed on the card. So
yeah.
So I don't know why I'm coughing. It's not Corona. You gotta clone this thing here. I think I'll just go text mode now. So. I'm crying. Sorry, it's not because of Eurosco. Yeah. So if you cloned that thing,
it builds.
Workspace, coin. Yeah, good. Pull. Very up to date. All right. Did I push it? Oh yeah, that's it. Thing. Yeah. So my throat. So this is when I loaded in IntelliJ. If you use ant, you can just run this, and then you should get a hello world. You guys can try this in parallel while I will explain what that does. Can I just turn my throat off and on again, something like that? I don't know if it helps. And I don't know what's going on. I probably need to pee like a lot. This happened during the London demo as well. Like, what the hell?
You've been smoking spliff?
It's been Justin. He smoked and I got, you know.
Yeah, Amsterdam.
That must be it.
Okay, maybe that helps. Anyway. Okay, so can you all see the code here? I hope you.
Yeah.
So yeah, so this file here is literally what will be loaded onto the card. No, it's put back there. Roscoe, can you just, and I do sign language, you know? I don't know. Let me whisper. Can you hear me whisper?
Yes,
okay, so we do that. This is horrible. I don't know. I'm very sorry about that, because usually I can't talk. So
just keep going and cough. It doesn't matter if you cough.
Yeah, but it's painful for me, you know. I mean, maybe you're into that. Yeah.
We're all developers here. Power through.
Yeah. Okay, I will just suffer through it. I'll be strong and I can do it.
Does Roscoe have any brandy in the house?
I don't know. Do you have
or throat lozenges?
Or honey? Do you have honey? Okay, let's try honey. So we try honey. I thought we should solve death problems here, not like problems like sore, like my throat. Anyway. So yeah, that kind of lose my train of thought. But anyway, so can you raise your hand, like who already developed any kind of Java, like wrote a class, anything like that, any Java? Oh yeah, like a spoon of honey, yeah.
I've written Hello World.
I don't know, Eleanor probably did.
Every day.
I'm not muted anymore. Yeah. Maybe it's very nice. All right. I will just eat this throughout, you know.
Do what you gotta do, man.
Oh yeah, thank you. Let me contemplate that plate. Good. So back to the class. So all the programs on a card are called on a Java card are called applets, and they derive from the class applet. So we just write a class deriving from the applet, and then we add the function install, and the install will actually put the card will actually initialize the applet on the card and do all the things. So what we do here, we call the constructor of the applet. It gets some parameters, but we ignore those, like install parameters. And there we initialize these two variables and actually initialize the whole thing. And what we have to keep in mind that the card has two kinds of memory. It has a non-volatile memory and it has a volatile memory. The non-volatile memory, this is very special memory, but the card has a lot of that, like 100 kilobytes or something. This is like sealed memory, so you can't access it from outside. Actually, the other memories, this as well. And if you power off the card, the memory will still be there. So you can, it's basically like a file system, more or less. You can store data there for a very long time. And they retain this data for a very long time because they have been engineered like that. And the other kind of memory is the RAM, random access memory. This memory is very fast. And the good thing is you can write on that lots and lots of times without any wear. But for the non-volatile memory, like the EEPROM erasable, electric erasable programmable read-only memory, something like that, you don't want to write that too often because this will wear the thing, so it kind of lose its like it might break at some point, which isn't too good. So we use the RAM memory, which is also faster, and these cards are incredibly slow, so we need to really squeeze out every little bit that we can do. So here you generate memory in the NVM with new. So this will generate a non-volatile memory. But for volatile memory, we use a built-in function called make transient binary. And we put those into these two fields, and then we can use them later. So this basically generates, a byte array of size 256. And we can use that to write the text, hello world. Like these bytes are hello world. Let me close that. Yeah, and we send that over. And the way we do that is we use like some built-in function. But this looks really scary, like a lot of conversion and stuff. But there's actually a certain pattern behind that. Anybody know what slices are, like in programming? I'm sure. Yeah, slices. Okay. Chris Jordan was shaking his head. So slices are basically you have a pointer to some memory and a size, and then it's basically okay. This is an area of memory that we are referencing, and this is very powerful. Like Go has that built in, Rust actually also, Java unfortunately not. So the way Java handles it, that you just have two variables. One is called offset, and the other is called length, and all of the functions in the smart card world have used these two variables. So for example, this built-in function called sendBytesLong, which basically returns values, returns something from the smart card, takes in the array of the response, like a byte array. But it also takes like, okay, where within this byte array does everything start, and how many bytes are we going to send? This might seem a bit superfluous because you can just maybe shorten the byte array or something. But these are all very expensive operations on the card. So we have this mechanism where we basically can slice into parts of memory like that. And we will see that throughout this whole presentation because it's literally everywhere, as you can see here. So here we got the array we want to copy. Here's the offset within that array, which is starting at point at 0. Here is the array we want to copy it into, which is this volatile array, which is called response. The offset where we start copying, which is 0 because we start at the beginning, and the length, the number of bytes we want to copy, which is just the length of our message. Then we send over the response, again, starting from 0 with the length we allocated, or the length of our message. And that's it. And as we can see here, if we run it, we get the string hello world, which is this thing here. I think you can also run it here. Yeah, maybe a bit on the invocation. So for that, I already set it up so it's more in line with what will come later, like the different steps. But right now it's just a register merchant card method that is implemented. And in here, basically all the smart card magic happens. Like in before, this is just, setting up things and handing errors. But here's where the actual smart card magic starts. So the first thing is that we actually select this applet here. So this applet has a specific applet ID, which is just some constant that we assign it. Because there can actually be multiple applets on one card, which allows cool things like switching between different possible things that you can do in the smart card. And then we transmit, then we actually call transmit and send over a appdo. And an appdo is an application package data unit or something like that. Application data unit. Very dumb abbreviation, I think, very not meaningful. But it basically consists of 4 bytes of information plus payload. This one is called class, this one is called instruction, this one is called parameter 1 and parameter 2. But usually I just use the instruction byte and set the rest to 0 because I don't know, it's kind of shitty designed, so I just use this instruction. I don't care too much. Yeah, so we call transmit, and what we get here is actually the response from the card, which is here. Like this thing that we send over here, this gets sent to this variable. And then we, decode it from whatever Charles said. This is in, I mean, it's ASCII anyway, so whatever default is fine. And we print that, and when we run it, here. Oh, it needs to code. Yep, we get hello world. Anybody, any questions so far? Because we'll get into more nitty-gritty stuff in the next step.
How would you describe slices again?
Slices. It's basically
like I remember in my Go course they taught it as like an array of a specific type.
Yeah, here it's just bytes. It's just bytes, like literally bytes. And generally in here you only have 2 kinds of data. I mean maybe 3, but you have basically 2 kinds of data. You have bytes, you have shorts, which are 16-bit integers, and then maybe some kind of class. So here it's literally just bytes. But yeah.
Yeah, so it's like when they would explain slices, it'd be like an array of type bytes.
Yeah, here in this case. Yeah, it could also be of short, but anyway, yeah. All right, anyone another question? Because this is a lot of new stuff, and I don't want to steamroll you with lots of concepts. Good, Chris Troutner is fine. All right. Marco is frowning a lot, or he's shitting. I don't know. Maybe both.
I'm drinking Earl Grey tea and just watching. I'm taking a passive role in this one.
Yeah, that's fine. All right, so the first thing we do is generate a private key on here. And this is actually super easy because, you know, it's built in. So we just add a new, I don't know, private, public, private member of this class, like a field. And for this, we use Bitcoin key. This is actually something I implemented, but it just reuses the existing, you know, EC private key and sets the Bitcoin curve parameters. So this is all boilerplate, and I use it in every applet, like I just copy paste it, and it's now public. You can use it. I haven't set the license yet, so I will sue you, and you'll have to send me pictures from there. No, I'm just kidding. I'll probably MIT license it or something. So this will be the coin secret key. Yeah, and we just, you know, initialize it with new Bitcoin key, like that. And then we actually go in here in the constructor and call generate. So in here we actually need a temporary array. Like this is a method I wrote, so it needs a temporary array for some public key computation. But we can actually just use this mem thing, which is kind of meant as like just some temporary thing where we can put stuff and then it later gets deleted or not.
Mem is the non-volatile volatile memory, right?
That's the volatile memory. This one is fast. And the important thing is this gets reset after you pulled the card of the thing out of like it's like if it's no longer powered, like if there's no power, then it gets reset. It actually gets reset a bit earlier, like on deselect, but this is a detail. All right, so let's just run that. And yeah, I mean, if it didn't work, then we would get an error. So for example, just to show you how that would look like if we were to do this. So we forgot to initialize this, so we would get a null pointer exception. Yeah, then we get like, unfortunately, a relatively unhelpful error, like a system exception. But this is just the way it is for smart cards. Like there's no easy fix for that because they are super dumb, so they have terrible error reporting. So the way you do it is basically bisect. You remove code until it works again, and then you add code back in again until it works. And yeah, that's kind of the tough life of smart card development, but I think there's no way around that. So we generate the private key, but we want to kind of know like the public key of that. So we copy this line, and then we say get pub key, what's it called, coin, get coin pub key. I think it's a good name. And here in this thing where we basically, like this is basically the main function, or I mean, it's called a process function. You get some data, you do some things, and you return other data. So we do it like this, and we just, where is it, get public key. Public key, yeah, because they're compressed and uncompressed. We actually need the uncompressed thing because these cards don't know about uncompressed, about compressed private keys. So yeah, it looks kind of old school if anybody's been around in Bitcoin a long time. But yeah, so this is the target we need to send it to. And this is the offset, like where you, within that thing. This is basically like the slice thing. But we just put it at the beginning, and then we send it back, which is actually more or less the same. From this function, we get back the size of the public key. I think we do we? Yeah, we get it. Yeah. So we can get the length and just get the length here. So now if we replace our function here. Instead of saying hello, we say get coin pub key. And say this would be the card of the merchant. You can get into that later. Merchant pub key. And then we do bytes to hex response. And if we execute that, we get an exception. And I don't know why. Oh yeah, actually, like this is the code for unimplemented or instruction not supported. And I did the classical case fall through error, which is probably a very newbie thing to do, but it happens. So yeah, this is the public key of the merchant. This is uncompressed public key. And this would then probably be stored in the point of sales system or something. Yeah, is everything clear here for everyone? Like any questions about this generation? Like, or anybody is like, okay, I have no idea what we're doing here right now. Good, Chris Troutman.
I have almost no idea what you're doing right now, but I'm enjoying watching it.
Okay.
It's late.
I'm following along at a high level.
Yeah, yeah. I hope I don't get too much into the nitty-gritty. But yeah, I think it's more about like getting the concepts of these smart card things. Because once
and just seeing what's possible on there, it's incredible.
Yeah, exactly. Like having a mental mindset about that. Because like all this slices thing is like very detailed things. Anyway, so yeah, now we got the pub key, and let's actually put that pub key into a variable here, private byte. Is that actually what formatted? So this is the merchant pub key, and we store that here. Merchant pub key. There might be a cat joining during the stream. Yeah, there it is. And it's eating my honey. So yeah. So the next thing is actually the generation of the shared secret. Is there anything else I missed? Oh wait, I actually have a battle plan. Yeah, secret sharing. All right. We're already getting into the fancy stuff. That is cool. So yeah, we just add a new method here, which is let's call this already move move coin secret key. But this will actually just generate a secret and generate a shared secret and then release it, which is kind of just for showing how it works. But we will. Those keystrokes were cat. Those were cat keystrokes. It's kind of cute, but
You're gonna be a programmer.
yeah. I don't know. She'll sue me because of copyright. Yeah. But for this, we actually need the internal private key. So this is actually quite easy to add. So just do internal secret key. And then also all that here. Internal secret key. And what we need to do here is actually enable we need to initialize all the variables for this key agreement, like the Diffie-Hellman kind of thing. Yeah, so here we can just call this internal secret and then share a secret. So here we have the, we need to have like, the way Diffie-Hellman works, you have a private key and a public key, and you combine those and you get a secret. And here we get a public key, and that public key we get from the input, which is the updo. So we just use this buffer, which is the updo. The offset is actually a special index, which is called CData, because there's some stuff before that, and CData is basically the actual payload. And so this is the first instance where the slicing mechanism makes any sense, where we actually say like, okay, we don't want to have this garbage before, but we want to start in here and then from there go on. The pk length, I think in Bitcoin key there's this uncompressed size. And then this is where we send the thing, like the shared secret to, which is in this case just a response at 0. So yeah, when we send that over, this is again boilerplate. Let's not forget the return here. And actually we need, like, there's some patterns that repeat. So we send that over. And now here we have to, call that. So this would be like the second card that we would invoke. Now we can copy that here. Right. Customer card. Move coin escape. Move coin secret key, and then we feed it the merchant public key. So yeah, we already got the public key of the card, and then we combine that of the first card, and then we combine that with the public key, with the private key of the second card, and then we just return that and print that, which is not what we want, but this is already moving us in the right direction. So this is the shared secret. Response. Send that over. This cat is really cute. So yeah, what we forgot here is that we actually have to also call this select applet thing on the card. And yes, I completely detected that from this code, so you kind of get used to this. Yeah, so let's run that again. And here we get a shared secret. So this is like if we didn't release that to the whole world over the over the up to thing, then this would be the secret that only card A and card B know, but nobody else in the universe except by chance. And yeah, this is already half of the deal. Yeah, but what we actually want is to move that thing. So we wanna, like what we definitely want to do is send over this coin secret key. So yeah, I think I'll just for like this is my cheat code. Sure. Yeah, we did the share secret. Yep. Oh yeah, we copied that over to this once. I don't think that's the right way to do it. Yeah. Oh yeah, but for that we need. Yeah, so we need those two things for encryption. I'll just copy and paste that because I don't know, it's not too interesting. So we need we will use AES for encryption because that's kind of cool. And then we use the cipher thing, which is for encrypting stuff. And we just, there's also, this is a lot of, boilerplate code, which isn't like, which you just do once and you can have it. So here with the key builder, we basically generate a key that can be used for AES encryption. It can generate all sorts of keys. It can also generate actually private keys. It can, like for public key cryptography, it can generate RSA keys and probably some other keys which are more fringe, but most cards can do that. Yeah, here we just use 128 bits, which is half of what we actually generated the secret for, but it's fine, we just use half of that. Yeah, because this one just works. Yeah, and then here we initialize the cipher. They're currently not connected, like they're just two different things, but we actually connect them in a second. Where do we do that? Here, init. Yeah, okay, so what we need to do is we have this encrypt key, which is the key, the encryption key, basically. Like, I hope most people are aware how AES works. So we have like a secret, and then you apply a key to it, and then garbage comes out. Then if you apply the key again with the same algorithm, then you get the plain text back. So what we do here is we don't write the stuff to the response, but instead we write it to our mem. And actually, let's just be sure. And I don't think this will end up in production, but just for my own sanity, we already wipe this thing. So we fill it with all zeros, mem short 0, and then what's the length, mem, and we fill it with zeros. Yeah, if anybody is very confused by this notation, this is just Java being Java. You know, you need to convert that. So yeah, we set the mem to our secret, and and as I showed here, we need to really make sure that this is wiped afterwards, because maybe it leads to some other method. Yeah. So we got that in mem at position 0. And then we can init our cipher with our key, this encrypt key, like this. And I don't know what this one is. I think, yeah, this is, yeah, mode decrypt or encrypt. So here we actually do the encrypt. So we, encrypt whatever is in there. And then I think we can already start encrypting it. Oh yeah, no, we need to first initialize what we want to encrypt. So here's where the slices thing again comes in handy. So we have the coin secret key that we want to send over, and we do get private key. So we actually move the private key, and we do that. We move this into mem, but we put that at position, I think it's not too important here, we just put it at position 32, which is like the length of the secret we generated here. So basically in mem we have the secret, and then the shared secret, and then we have the coin private key afterwards, neatly packed. I mean, we could also go do stuff like 40, but I think this is fine. So yeah, now the thing is in here. And now we can call the cipher, and we can actually feed it bytes after like repeatedly with update, but we have a very short cipher text, plain text. So we just immediately do final. So this is like basically the final round of the encryption, and we don't do any rounds before that. And I forgot the order of those. So yeah, the input comes first. Oh wait, this is the one. Yeah, the input comes first, and the response comes later. So here we say, okay, and encrypt this thing. And in this case, this is the private key, which is at position 32. And it is the length of a private key, which here is just secret key size. And this we put into the response. Like, this is what we actually return from our thing. And we put that at, at the beginning of the thing. Yeah, I think that's it. Do we have some things here? Some wiping? Oh yeah, and actually we reset the coin as came. That's like the whole idea. Like this is all we've worked for. This is the dumb thing that makes all of this possible. Yeah, and here we also have to provide a temporary memory thing, which just wipes stuff, which helps wiping stuff. Yeah, this basically, like the code there is just, it first wipes this thing, and then it sets with zeros, and then it sets the private and public key to zeros, basically. Yeah, so let us call that and pray that it will work. Yeah, so this is now another random string, but as long as the thing doesn't crash, we know that it at least generated us something. The only thing we need to do is that this is no longer a shared secret. This is now the encrypted private key. But just for, you know, a bit like we kind of like dealing with a black box here. So let's add a, just for testing, add a leak private key thing here, which we don't want to have in production, obviously. But this is why I named it this way. Maybe I should put debug in there somewhere. But yeah, and this is basically where we just return the secret key. Maybe I should leak coin SK. Yeah, so coin SK, and where is it? Get private key. Put that in response. By the way, the honey worked wonders. I don't know, like if you learned nothing from this, if you got a bad throat, it's honey. Yeah, does this return to length? Yeah, that's a common pattern, that things that do things with bytes, they just return the length of the thing. And yeah, I don't know, it's kind of a weird sentence. Anyway, those who are smiling at me. So yeah, so let us leak the private key here. Merchant card. No, no, this isn't. We want to, the merchant card is empty. Yeah, we want to have the customer card. So but we want to have that before we wipe it, of course, and after. Secret before. And this is the leak without any payload. I mean, it wouldn't matter if you sent that over. And then secret after. Let's just print this. After, all right, let us run that. And taking a bit, let's get some more honey. Yeah, that's what we want to see. Like we see the secret before, and after we ran this thing, it's wiped, and we no longer have the private key. All right, but now we also want to, you know, move this thing to the other card, like basically redeem this encrypted thing. I'm not sure how to decrypt it, to write it, but I would just say, I would call it redeem encrypted coin or something. And this shall be number 4. Oh, by the way, like before I jump into that, this probably was kind of complicated. Does anybody have any question on that? Even if it's super dumb, like how would the Amish deal with this or something? I know that's a dumb question, but yeah.
Well, so you said that this whole scheme is heavily reliant on Diffie-Hellman key exchange, right?
Yeah.
One of the things that I didn't get, like I know I've studied it before, but is it possible to give just like a quick 30-second overview of Diffie-Hellman key exchange, how it works and maybe how it's different from other things?
Yeah, so basically it's just multiplying one key at one curve point with the other private key, and that gives us a new curve point. And due to the associative nature of elliptic curves, you can either like if you do it with private key, public key from one party, if you do that operation, then it's the same thing as if you do it with like public key and private key reversed from the other side. I'm not sure if that was a great explanation, but you're nodding and smiling, so I think
Yeah, that helps. That's helping to refresh my memory. Yeah.
It's basically abusing. I mean, not abusing, but really using the associative nature of coin multiplication. Yeah. So we have one point, multiply that by private key, and if you do the same thing with public key and private key from the other parties reversed, then we get the exact same thing due to that associative nature. All right. Any more questions? That was a very good question.
So public key A plus private key B would generate the same secret as private key A plus public key B.
Yeah.
And you can have the same encryption key and use symmetric cryptography based off of public and private keys in a trustless way, right?
Yeah, exactly. You can do symmetric encryption with that. Yeah. What we do here? You could also use some because there are elliptic curve encryption algorithms that use the curve directly, but I don't know. I don't even know if the card can do that, and this is kind of more my style. So I just did it. Yeah. Any more questions on that? Yeah, all right. So otherwise we move on. So now what we do is we restore the secret or the shared secret on the other card. Not restore, but also generate it and see. And then we can actually see like, oh yeah, actually this Diffie-Hellman thing, like it's actually a thing, it actually works. So what I will do is I will actually add a new thing that will just leak again this shared secret just for debugging. So I will do a leak shared secret. So this is like if this were to be on the card, then the whole thing wouldn't work anymore. Or like the incentives and stuff working. Spawns and so we basically do the same ECDHA thing, ECDH, yeah, sorry, as we did before, and yeah, we shouldn't release that, but we just do because for debugging. Yeah, so let's print that here. So we leak a lot of stuff, but that is fine. It's not real. I'm gonna leak shared secret. Secret. Let's do it here. Oh, this is not German. Shared. In German we say CH for sure. I'm not sure if that was too helpful. But, yeah, so this would be the shared secret. And if we now do the same thing on the other card, then we would expect both of them to be the same. So yeah, let us just do that. We have redeem. We call it redeem encrypted coins. Do you have the branch for that already? No, we don't. Okay, so I will, generate the shared secret again, and yeah, I think we can just. I think we can use the leak again here. Yeah, let's just use the leak. So yeah, merchant card. We also need to store the public key of the customer. So this would be like stored on the point of sale system, and at some point the merchant could come in and redeem all the encrypted stuff, and this would have decent UX. It wouldn't be That would be kind of cumbersome to, you know, okay, customer, you do your card, then merchant, you do your card, and I don't know, it'd be very awkward, but we don't have to do that actually. So customer card, and this is the customer public key. Public key, everything is the same. And here we can just, you know, do a shared secret here, and here we reverse merchant. And here we don't send the merchant, but we send the customer, not customer, customer public key over, which we store here. Got the shared secret, and we print that. Let's actually enable that a bit better. Shared secret merchant. And this is shared secret. No, this is merchant. And customer. And if we run this, we get an error. Ah, because we need to select, maybe. Sure. But I don't think we need to. But it's always nice. Really. No, wait.
Question.
Okay, maybe I need to. Oh. I think here I missed. That means, oh, it's still the same picture secret. Yeah, this is just the. Oh no, it's a different error. Oh no.
Are you supposed to not be using length in the redeem command?
Yeah, length maybe. This one?
No, two more above.
Yeah, I haven't implemented that yet. Like I wanted to first do the shared secret thing here.
Gotcha.
But apparently that. But yeah, good catch. Because this usually means like not support. Oh, maybe we did the. Let me just, you know. Yeah, so this is a website where you can look up errors and internal exception. More exact diagnosis is not possible. Okay, this is a great error. Yeah, sometimes you encounter this stuff where it just says like, oh, yeah, there's some error. And
so this is basically an SDK you get in Java for these specific cards you use?
For Java cards, yeah, and they're kind of common. And you can literally order them from the internet. Alibaba, I got those from Alibaba. They're not very expensive.
Oh,
they just take a while to get, and you just need one of those markup readers. They're like this one is a bit more pricey, but they're big ones that are just as good.
But you couldn't like develop for these cards using C++ or Rust because you don't have the development.
Yeah, it only works with Java because yeah,
right.
That's how Java operated in the past. Like Sun or Oracle or whoever did that, they were kind of smart with their tactics and stuff. Yeah, I don't know why I just throwing that thing. There's no literally calling. Maybe it's the internal SQ. We're literally doing the same thing as above. I are confused. Yeah, this one is here. Everything good. Maybe just print the. We don't want a coin public key, we want internal public key. What are we doing here? Yeah, we need to, first of all, we need to switch this out. Yeah, so for some reason oh yeah, for just for demonstration, I put the coin public key here, but actually we don't need that. We want the internal public key here, because this is how we generate the secret. Internal public key. I mean, we would need it for checking like if it's actually on the chain, but we won't do any on-chain stuff today, because that's kind of out of the scope here. So yeah, we send over the internal public key. I'm not sure if that's the error, but yeah, I'm really confused. Otherwise, I'm very confused. Maybe because we reset the thing. Merchant, no, but we didn't reset the merchant card. Yeah, if we do this, then it should stay in. Oh my God. Yeah, sometimes you get stuck in this place. If anybody, like, you know, is following along and doesn't have this error, you can, you know. Oh, actually, that was the error. So why did it reset the merchant? So yeah, so here the error is that we, for some reason, wipe the internal key of the merchant card. Because if I delete this, it works. And usually this error was like null pointer exception. So we got, I think the name wrong. What? This is a scam. Okay, this entire thing is a huge scam. Like, I don't know.
You didn't run make clean, does it?
Yeah, make it clean. I don't know.
Yeah.
Probably, I don't know. Like this sucks. Anyway, it'll probably just recompile. All right, so I changed nothing and it works, which is cool, I guess. Yeah, so now now I would be excited, but I'm slightly upset anyway. The shared secret from the customer, as we can see, is exactly the same thing as the shared secret.
Yes.
Which is exactly what we want. And this is the magic of Hippie Hellman. Yeah. And just to, you know, nail that one more time, here we send over the merchant public key to the customer card. And here we send over the customer public key to the merchant card, and we get the same shared secret. And nobody else has that. I mean, currently we're leaking it, but yeah. So now we can actually implement this thing, which is what Josh already was complaining rightly about. And I kind of, I need a reminder how I did that. Yeah, oh yeah, so we share the secret again, but this time we also have an encrypted thing. Let me just, you'll forgive me if I just copy paste this. So this is basically some helper constants who are like, okay, yeah, we slice again. So in the input, the secret is the first 32 bytes. And then after that, we get the public key, which are the next 65 bytes. So this basically sets up all the slicing stuff. So yeah, so we again share a secret actually. But this time with a different index, public key index. And we do put that secret again into mem at 0. Yeah, so the length is that secret size, and it's at mem. Yeah, and now we need to decrypt. And here again, yeah, so we again initialize our key. And this time we have the secret again stored in this mem thing. we initialize our AES thing, but this time we don't encrypt, this time we decrypt, and there's a nice mode for that. And do we need to add something else? No, we can jump right into it. Show secret, yeah. We can just do final. And this time this will be interesting because we will do everything in mem. Right? Yes, so no. This is actually like where the secret comes from, is from our input, which is buffered here. And here we, you know, our encrypted thing is 32 bytes long. And yeah, this is basically a slice onto the secret signed by the other card. And we want to decrypt that. Yeah, so this is that thing doing, saying like, okay, this is the thing we want to decrypt, please decrypt it. And the next thing is where you want to write that. And I think a good place is also mem, but again at position 32. So here we got the private key is now at mem 32. And I think we just now, it's it basically, yeah. I mean, now we have this secret key, we call it coin sk. We do set private key. With this dot mem. Is that it? But this time with the short here. Yeah. And then we just do wipe voice cleanup. Yeah, here I use response, but we don't use that here. So this is again just wiping the mem thing so we don't leak anything later on. And I don't think we need the length of the secret. Yeah, so this again, like here we share the secret, which we already, you know, did plenty of time. We initialize the cipher with this shared secret and use the decrypt mode. Then we decrypt the thing which we get from the point of sales in our updo. And we store it at memory position 32 in our memory, in our mem object, mem array slice thing. And then we extract from mem the private key and set it to here, to like this internal coin secret key with this function here. And then we wipe everything and we return. Yeah, so we can actually try that out, and then we're basically done. And we actually have some time left. But in case it works, maybe we take like half an hour to debug this small. So probably Roscoe has high expectations, and we don't get any response there actually. And we remove the leak stuff, maybe, I don't know. You can ask Snowden. So yeah, this thing is a bit more complex. Yeah, did I have two concat? No, I didn't have any concat thing. How did I have it here? Yeah, okay. So this is just a helper method to, you know, concatenate 2-byte arrays, because apparently that's not something you want to have in your standard library for some reason. No, which is concat. So yeah, so remember this redeem, it needs two things. It needs the encrypted private key, and it also needs the public key of the customer. So we put that in here. We have the Oh, we need to store that actually. I forgot that. So this would be the encrypted secret, or encrypted secret key. And we store that here. Secret here. And here we put first the encrypted secret key, because remember, this is the first half of the thing. And in the second part, we put the customer private key, because we're sending this to the merchant part. So yeah, we don't get a response. We can just drop that here. But what we actually want to see is whether we transferred the secret correctly. Secret opt-in. Merchant. We again leak the secret merchant. We leak the secret coin, secret coin thing, whatever. This is the merchant secret key. So we run that here. Getting a bit complicated now, but yeah, that worked. Crazy. This is not expected, so it just works. Why isn't there some random error that just screws everything up for no reason? Yeah, so we leaked the private key here. Then we transferred it, and it got wiped. Then this is the shared secret, and now the private key is transferred. So you could send money to this private key, then send it over with this mechanism, fully off-chain, actually fully offline if you wanted, and then the secret has been transferred. Pretty cool. If you don't find it cool, that's totally cool. I think it's pretty cool.
It's pretty cool.
It's very cool.
Yeah. Somebody's tapping. Thank you.
That would be Eleanor.
Thank you, Eleanor. Let me move that to this here. So, anybody have questions? Probably.
So yeah, so just again, I was only following along at a high level, but so you've got the secret key before. You show that it was wiped from memory with all those zeros, and then you pass the shared secret to the merchant, and then they're able to regenerate the private key from that shared secret.
The encrypted private key. So we encrypt the private key.
Oh, okay.
And then we send that over. This shared secret, I mean, if I delete it, then it might be a bit easier to understand. But this shared secret,
the merchant uses the shared secret to decrypt the private key.
Yes, exactly. And he can generate that using Diffie-Hellman.
Okay.
And I think we actually need to wipe the public key here for security. Because then you can just send it right back and have the double internal. And we need to generate a new one. But yeah, this thing is horribly insecure anyway. I think somebody had a question.
No, I said start again.
So
yeah.
Like what? Just do it again.
So today
one more time from the top.
Talk about private key teleportation,
okay.
which allows
where's
offline transactions.
Where's the starship?
I'm
sorry.
Yeah, we'll do it cleanly this time.
A serious question: who's the user in all of this? Like, am I gonna? Who am I doing this for? Like, if I was now onboarding people to this, who's the target group here?
So the target group are people for whom it is very expensive to do on-chain transactions. On the one hand, I don't know who that could be. And
Wait, did you say expensive on-chain transaction?
Yeah, I have no idea what that could be. And I don't know any chain.
I mean, for people who want to trade pre-fork Bitcoin keys, that would be something.
Wait,
or maybe people in Australia with no internet connection,
for example, or people who are
pay for a meal,
or Amish, or people who are very concerned about privacy and they're able to establish a kind of secret channel between each other, then they can send money from between each other without. So maybe drug dealers and like drug cartels and criminals and stuff. Yeah.
The forgotten man, basically.
Yeah, people lost in the middle of the South Pacific, but still need to spend Bitcoin cash.
Exactly. Or like if you like for intergalactic trade, like we just lock some points into these cards, then you can go off to Alpha Centauri and still trade BCH, and just return like every 2 kilo years and redeem those coins.
Yeah, but you have to communicate anyway, right? To say, hey, I
Yeah,
sent you
would,
money.
for redeeming, you would have to communicate, but you know.
So there's a problem with time travelers and block time, though.
Is that a question? I didn't get it.
What? No, that was a sarcastic remark.
Okay, yeah.
Yeah, I do have a thought for you when people are done with more serious questions. I think I thought of maybe not a great solution, but a solution with the. I wasn't quite following like all the cryptography stuff in Java. It was a little hard to read the screen also, so it's like I was like gnawing in the back of my head over the problem of the double spend and stuff like that. But I'll let it wait until other people have more direct questions.
Yeah, it's basically a different solution to the double spending problem, just using completely different tools, like completely different.
Thought I had was this, right? Was if you had like private keys that had set amounts, like $10, $20, or 0.1 VCH, 0.1 VCH, 0.001, whatever, then you could have those be maybe tokenized or something, where you use cache script of borrowing ideas that are just watched hopefully correctly, that apparently can know its block time. So the block time it was created, and then say for, I don't know, 1,000 blocks then on was about a week, it would be active, and at which point it could be automatically redeemed back to the wallet it came from the card with, which would only work for someone who was just temporarily without internet access or whatever, but within the next week would have it, because if someone other than the key that generated it ever tried to cash that in, that would probably be a legitimate merchant, and that the thief would be the double spend. So it would prioritize a key that was, what would be the same key though? You know what? It would have to be multi-sigged with something else on the card, I think, for that to work.
I don't know. I feel like the cryptography kind of got over my head together.
No, I'll piece it together and send it to you. My brain is not fully functional right now, so
yeah. By the way, sorry for the kind of weird presentation in the beginning where I was walking around in Amsterdam, but I think it was kind of.
You did good. You recovered. Fought through it.
It's fine. I didn't even notice you were walking around Amsterdam until you walked into an apartment.
Oh, cool. Awesome.
Yeah. So, did you get a kiss from a Dutch girl? Is that what happened there?
Or what? Say again.
Did you get a kiss from a Dutch girl? Is that what happened there?
I think it was Leonor. Yeah.
Oh yeah.
So that's all recorded now. I'm sorry.
But she's not a Dutch girl. So.
Oh, yeah, she's not a Dutch girl, so it doesn't count. Yeah.
Oh, I see. Yeah. No, it was at about 1 frame per second, so it's like.
So just 1 frame of Dutch girl. Okay. Or not Dutch girl, depending on how Roscoe.
Who did you deny the kiss to?
Justin, but I don't know. That was kind of rude.
I'm gonna go ahead and stop recording.
I would be offended if you denied me a kiss.
Oh no!
Smoke
That's getting all political. Want to have a cookie, Roscoe?
No, leaving is cookie. One of them is yours, one of them is cookies.
Oh, true. Yeah, I'm confusing ownership of cookies. As long as I don't confuse ownership of private keys.
Christian, I think you have control of the recording, since you're the host.
But I also pressed the record button.
I don't know. It says I'm still recording. Oh,
Another thing, Tobias, the
Okay,
SDK for the card comes with a simulator that you use to write this program, or did you have to write the simulator yourself?
Simulator is open source. I mean, it's open source, but they don't have a binary released. So I just compiled the binary myself and put it into the repository. Not binary, the jar. So this is the jar that it connects to. But it's fully open source, just jcardsim. You need to use the most recent version, because otherwise it can't do Bitcoin signatures, which is kind of boring.
Yeah.
But these parts, they can do Bitcoin signatures. Obviously, otherwise it would be like I would be like scammed with it the whole time.
Yeah, Bcash would be a thing.
These cookies are amazing.
Really good, right?
Should we wait in the stream until they have an effect on Tobias?
What?
Oh, I'm assuming these are drugs.
Oh, are they weeds?
No, no,
Oh
no.
no. Okay. I don't want to,
well,
spoil
so
You never know.
company
It's empty then,
secrets.
so.
this is really, I wanted to clarify that. So this is really, you got two, like I have a card and Tobias has a card, and you can transfer a UTXO from your card to my card. That's essentially
Exactly.
just demonstrated here.
That's the elevator pitch that I'm unable to make.
Okay, yeah, and so there was no blockchain needed. It was just you and me and the device that was able to, we plugged our cards in and did the transfer. Cool.
And this would work with any Java card, right? Like you could use
I mean, those that
like cards
support
with those mag strips on the back rather than NFC.
Oh yeah,
Mag
you
strips
can
can't
you
do
can use both
cryptography.
both chip and like this one has both. Like it has an antenna that's going around there, and it also has the chip. Maybe you can show it.
It's basically an NFC, right? Just
this one has
or is
both.
it-
This card supports both NFC and
Yeah,
contact.
it's they're two
With
different
dual
things.
interface, you can find them on the internet. They're not too pricey. Let me show you that real quick. So this is my phone, and this is the card. And I just hold the thing here, and you can see like there. I don't know if it doesn't really work because we humans have brightness correction, but this thing doesn't. So, but you could see like a little antenna there shining through.
I think it's something.
Anyway, I was hoping for a more powerful.
The biggest problem is how to assure the atomicity of this exchange, right? I mean, how do you trust that the card that you just swooped a private key to you actually deleted it from itself? You would have to talk to each other in some way.
Yeah, there are transaction mechanisms on. Oh yeah. Yeah, but I wanted to show like the whole antenna that's going around the thing. Oh yeah, perfect. You're doing my job. You're hired.
Cool.
What was your question again?
No, I was just talking about how it's odd to trust that the private key is going to be deleted in the first card.
There's like a transaction mechanism on Java card.
It's got to happen everything or nothing.
And if you like power off the thing at a certain time, then it just reverts the whole thing, and you don't get the response, and you're safe basically. I think a bigger issue is that you not that you can trust, because here the way I wrote it, like we actually delete the private key before we send anything over. So the bigger issue would be like if you were to power it off too early, then the secret key would be just gone into nowhere, and we would have useless UTXOs on the blockchain, and Amory would be unhappy.
We don't want that.
It's okay. Craig Wright for this statement.
Yeah. We need to change consensus about who owns these UTXOs. More cheap.
Well, thank you, Tobias. This was actually really cool to see the Java card in action. So thanks, man.
Yeah, you're welcome. You're welcome. this is all recorded. Probably put it online. And you can, see it again. It's interesting. And if not, then no hate. We're still cool, bro.
Here's a question, because I just thought of another potential snag. Right, someone might duplicate the key before spending it. Right, I mean they might duplicate the entire card, right?
No, that's not possible.
It's not possible to duplicate the card?
Yeah, because due to design of the card, like that's one of the key properties that are done by the card. Are done by this technology. That's why I'm making this presentation. Like this technology is actually kind of insane for blockchain people, because it has like these really cool constraints and features. It's like on blockchain, you basically have trusted code, and you have you basically have trusted code. That's all. But everything else is completely public and completely auditable. With a card, you don't have as much trusted code. You kind of have trusted code, but you never know what's on there. But you can have mechanisms that make it more trusted. But what you have to, everything is completely sealed. Like you have this black box, which you can do computation in, like any computation. It might be slow, but stuff what we did there. And you can release some of those into the public. So for me, it feels like there's like really this nice complementary, because on the one side, everything is public and auditable and visible. But on the other side, you can actually do things, also computation, but in secret, and only release stuff that's interesting.
Both the memories are inaccessible from the outside, right? The EEPROM and the volatile memory, or just the
both.
That's pretty powerful shit.
You would basically destroy the card if you want to open it. That would wipe the memory and stuff. So that's kind of the security model behind that. So
how does Java interface through like a serial connection? Because I know you can.
It's a
sorry,
USB.
what?
It's USB. So this one is
right.
USB.
But I almost wonder if you can send serial commands to access the EEPROM.
No.
Oh, USB does mean universal serial bus, so it is serial.
No, it has like a specified standard. I think for these things it's called PCSC. I don't know what it stands for. Probably SC stands for smart card. Yeah. What else? It's I think the way it works, if you're on Mac, you buy this thing, you plug it in, and you run commands. If you're on Windows, you need to install a driver. That's fine. You can also send commands from Python, which is really, I think the T is probably yeah.
Oh, okay. I got it.
If you want, I can install some stuff on the card, like the applet we just programmed. I probably can't run command. Maybe I'll run this stuff on the card, at least some of the stuff, just to know, like, show you how that kind of works. We'll do that. Yeah. No way to. Maybe this one. But too many smart cards. So this is an example of a smart card, and I will just put this in here in the smart card reader, and I plug my USB thing into my USB port. You won't need to see that. I think the T tea is consummated. We've got a direct causal connection there.
You allergic to tea?
I mean, I drank it the day, like the 2 hours before on a 2 hour. I swear it was.
Yeah.
See, I'm smart. Yeah. All right. Continuing with coughing. So it's not Corona. You're all safe. It's the tea. Let me use that.
You don't know if it's Corona in tea.
Oh, maybe you gave me Corona in tea form. I don't know. That's not very nice after you, Roscoe. I can get over it. So yeah, I forgot what the build script command is called. Yeah, so basically we can do it in steps. So we've got this target called build cap, and this cap, I don't know what it stands for, but it's basically a file. I need to build failed. I think the
Oh, Java has linker errors too.
working. Okay, so for the different word, like there's some class path issues, which are always very, very nice. Yeah, this is great. Okay, so I haven't fixed the class path issues. Oh yeah, this is the class path, right. And I need to put that to yeah. No. Okay. Yeah, so there are some class path issues, as I said, which I don't get. Or maybe I'm using the wrong version. AES redundant costs. Not fancy attack AES. Maybe I'm using yeah, I'm using the wrong. This expensive. Maybe I need to use this one. You know, a different SDK. Yeah, and now it worked. Okay, that was the issue. So not all cards, like they're releasing new cards and they get new cryptography things. And it seemed like the older ones didn't have AES encryption. But the next version, which is this card, it's the same version, like it's the 304, which are relatively cheap, does have. So we have to be, when you order these, you have to be really careful that they actually have the capabilities that you're looking for. So yeah, so this is still, it's still in there. We issue the next command, which is installing the file. And this is basically that. So we need to see that here. It's blinking. Upload it. It takes a bit too long for my taste. And that's it. Oh yeah, okay, so this. Yeah, sometimes these cards return not transacted, which is a very weird error. And I tried contacting the manufacturer and they don't really know what that is. And yeah, I'm still figuring that out. And right now my solution is to just take out a new Java card and try again, which is not ideal, but we need to make compromises. So yeah, I put it in. It gets detected. I run the install command. Load the cap. At this time, we won't get an error. Again. All right. So it's for some reason. Maybe these two were already, I don't know. So let's try again. And our retarded system fails, but that's okay because it wasn't real socialism. Yeah, I don't know what's going on there.
Third smart card is a charm.
Yeah, it's kind of upsetting. Okay, I don't know what's going on. Like, maybe the wrong version or something. But yeah, I don't know. I got all the. Oh wait. Maybe it did work, and it just threw an error. So we can actually use Python to access these things, and for that we use py as card. No. That's not fun. Oh, my recreation.
I think you need to bring the virtual environment.
No, I don't think that's the. I think I just forgot the. But I think I got a. Yeah, I got a Jupyter notebook. The other one. Jupyter notebook. Oh, but it just oh yeah, that's where it verifies me. IS card, so maybe I just didn't install it. Is it that cannot be? Okay, it's already satisfied. So did I type it wrong? Oh, I know. They were douchebags, and the module is named differently than the thing you import of. So it's called just smart card instead of PyS card. So yeah. Import. Yeah, all right, great. I don't know what's going on there. Readers. I've got those two, and one of those is the NFC one, and one of those is the contact interface one, but I don't know which. And I think we need to connect here. No, oh, this is a string. Damn. This is maybe let's just go through the tutorial. I thought this was easier. Oh no. User's guide. Oh yeah, it's readers. No, but where from? From system. These very self-explanatory things. So ours. And let's just try the 0th one. And let's connect. No, it's not. It is create connection. Awesome. Yeah. Okay, cool. So in here we transmit. It's called transmit. Oh, we need to call, and here we need to call connect. Awesome, great. And then I think it's called transmit. Yeah. And for that we need a select. No. Have to select. Oh yeah, so it's this string here. Yeah, so this is basically doing this. Okay, use this applet. That's the command. But here we need to actually put the applet ID, which I think is just, yeah, just 1, 2, 3, 4, 6, 7. Actually, syntax. Oh, come on, let's see. That's an error. Maybe this isn't right. Yeah, but this is basically like I'm now sending stuff to the smart card. I'm not sure if that's each this. So we're getting the same thing. Yeah, so maybe the transfer did actually not work. I'm not sure. Secret. Yeah, just trying things. Okay, that worked. So why does the install not work? Version and offset. Probably maybe we're generating too many keys. I don't know, like maybe the card is overwhelmed. Might be kind of sad. But yeah, we can try that. Or maybe no. No, let's just no, let's not this one. Oh yeah, I'm already over time, so yeah, if people want to leave, that's fine. Does anyone have, any more comments and stuff?
Thanks, man. It was awesome. It's really, really interesting stuff. Thanks a bunch.
You're welcome. You're welcome. And if you want to try this, just buy a card or a couple of cards. It turned out like this is indifferent from cards. And a reader, then you can start hacking actually on this thing. Or you can just, do the repository. I will publish this code on this repository. And you can try it for yourself. All right, but let me, try to debug a bit more, and then I think I'll go to bed.
This is great, Tobias. The good opportunity to see how the sausage is made, man. You've been working hard on this stuff.
Yeah, there's been a lot, and a lot of this stuff.
Yeah, I'll get another card reader and I'll try this. I'll try this code. Yeah, I'm sorry
I've been out of commission. I had a serial family disaster. So, which some people probably know about. But anyway, so first my mom got sick, she died. My dad got sick, he died. And so that's my wife, my mom, and my dad, just one after another. Nobody had corona, but you know, so I've been kind of out of commission.
Sorry.
Anyway, I'm sick now, so, but I also don't have corona. All right, so, but anyway, yeah, so I'll, you know what, I should order that card reader though. It's one that you
Oh,
sent me.
your cameras.
Yeah, the one I got didn't work for some reason. I don't know. I mean, I don't know why it didn't work. I bought some cheapo card reader, just couldn't get it to do the thing. Is someone recording all of this?
Yeah, I'm recording it, and if somebody else is recording it, that's also great.
Yeah, I mean, someone can put up a video so it can go through the how-to of the code here.
Yeah, I actually tried to stop recording, but it said I don't think it will stop until we end the meeting.
Oh yeah, all right.
It seems that the AES is making trouble on the card. So yeah, maybe we can look on the specs. Maybe we can put it. The AES isn't really like. Oh, you can look at that. Yeah. Is it okay for just anything I need to do? See you tomorrow, and thanks so much for being awesome. Yeah. Cool. So yeah. Oh yeah, we already. Yeah, I think I had like a whole pipeline for that, and I'm just calling everything manually right now. But yeah, what I'm doing here is doing the standard, like this is the standard smart card debugging. Like when I actually use smart card, it's like trying. Oh yeah, okay. So here now we know that this line of code is causing trouble, and it's probably because we're using an algorithm that is not supported. So yeah, I mean we could try with length. Yes. Not sure if making it longer makes it any better.
256.
Yeah, that would be probably more appropriate. Let me just look at the specs. No, what is happening? Yeah, so that card is the one I got. Maybe you want to write that down. I think the key sequence of letters you need to remember is this one. 3H145. The good thing here is.
Paste the product link.
Pardon? Oh yeah, I can paste it. And here we can see it supports ECDSA up to 521 bits, which is a bit more than we need for Bitcoin. Here's the RAM.
AES 256.
And this is a dot, so this is 2000 bytes. Yes. Yeah. Oh, maybe just. Yeah, up to this bit amount, it should be able to do that. I mean, maybe if we make it bigger, I mean, it's kind of dumb, but you never know in this kind of world. Or no, that one. Let's not make it fail even harder. I think I don't. I planned it as an update. Yeah. So again, cap is like a jar file for a Java code. So apply some. So let's see if it doesn't look good. It's blinking irregularly. Damn it. Okay. It would be kind of sad if this thing doesn't support AES despite advertising it like that. Or maybe I'm doing it incorrectly. Yeah, I don't know. I'm kind of at a loss here. I mean, it works on a simulator. So yeah, probably I just call the card manufacturer. But, kind of a deal breaker if the card doesn't support it, but you know, there are other cards out there that should support it. And, yeah, probably should have tested this before, but I was kind of on a timer and getting all of anything in there. So. Yeah, I think we ended here. It's been 2 hours. It was quite stressful in the beginning, and then it got pretty cool in the middle. And then now my brain is kind of fried. And if you have any questions, you can contact me. Probably just on contact@p.cash. I think that's the best way. It's on my website.
What time is it where you're at?
3 a.m.
Whoa.
Yeah, and for some reason my brain still works. At least I believe it does.
You're a trooper, man. Appreciate you putting it on.
You're welcome. Yeah, but that was very nice. Yeah, you've been
powered through the sore throat.
Yeah, that kind of worked. Yeah, this is giving me Vietnam flashbacks to the London presentation, where I was like 10 times more nervous because I was scheduling a live demo with Roger and stuff. Whatever.
Can we hear you sing a little tune?
Oh, this is too late. Like all the neighbors. I can maybe. Let's make a different live stream, like a karaoke live stream, or we'll see in some conference or something at some point. Yeah.
Sounds good.
Yeah, we'll start a quartet at the next conference.
Yeah, you've got the lyrics like they're on the internet. I think especially the All Hail Armory. I think that would that's kind of mandatory. Like, if you don't know that, like, why are you even coming to this age conference?
Yeah.
I mean, the ballad one is kind of long, so that's understandable. If you don't know. But you should know the refrain. Anyway, was a lot of fun. I hope this inspired people to try out some smart card stuff. And I mean, some stuff was kind of discouraging, like failing of the EAS, but all the other stuff, it's working. And Bcash is working, unless I'm a total scammer, which I'm not. And yeah, and that if you want to make that as a job, then just write at contact@p.cash and be like, oh yeah, this is actually super interesting. Can we figure something out? And I'll get I get funding and we can hack something together. And yeah, that is what's going on. I don't know if that's a very inspiring speech, and my brain is kind of fried. Yeah, taxation is theft. And have a good night.
Right on, yeah. Get some sleep, bud.
All right. Bye, everybody.
Okay.
Bye.
Thanks for the talk. Bye.